Welcome to the deep dive. You've brought us something really fascinating today, possibly, well, revolutionary, this motion theory of everything, and specifically how it impacts what we think our telescopes are seeing. It's based on this text, the Photon Delusion.
That's the one, yeah.
Okay, so it sounds like we need to forget pretty much everything we learned about starlight traveling for ages across space. We're diving into something quite different here.
That's definitely the idea. And what's, really provocative about it is this core suggestion that our whole way of observing the cosmos, it might be based on a misunderstanding.
A fundamental misunderstanding.
Potentially.
Yeah.
We're just so ingrained with this idea of telescopes catching tiny particles of light, photons, right? But this material challenges that right at its foundation.
Absolutely. I mean, for over a century now, the standard picture is telescopes detect photons, little messengers from the past.
Billions of years sometimes.
Yeah, traveling all that way, hitting our detectors, and boom, an image of how things were. And more photons means brighter, less means dimmer. Simple.
Well, simple seeming anyway.
But the photon delusion says that whole story. It's flawed.
It argues it's flawed, yes. Now, the conventional model, the photon model, it's been incredibly useful, obviously.
Sure, built astrophysics, practically.
Right, quantum mechanics, understanding energy packets, it all seemed to point towards particles.
Yeah.
Detecting those discrete hits,
Okay, but hold on. This is where the motion theory really takes a sharp turn, isn't it?
It completely flips the script, yeah.
It says telescopes aren't just passively sitting there catching old photons.
No. The idea is they are actively resolving something. Rhythmic motion, like structured vibrations that are already present in this fundamental motion field.
Okay, wait. So like ripples on a pond? The telescope feels the ripple. It's not catching a drop of water that flew across.
That's a decent analogy, yeah. The motion is the phenomenon. It's not carried by a separate particle. And the big implication...
No photons actually traveling those distances.
Exactly. No travel time, no light-year delays in the way we think of them, just resonance. The universe is like humming with structured motion, and our instruments are basically tuning forks.
Wow. Okay. So what's their argument against the photon then? Why is the old story supposedly wrong?
Well, a core point they make, and it's pretty compelling when you think about it.
Yeah.
We've never actually seen a photon in flight, have we?
No, I guess not. We see where it starts maybe and where it ends.
Precisely. All our detectors, everything we have, it just records the final interaction, that click in the sensor.
Yeah.
That's an event. It's energy-changing form. But is it absolute proof that a tiny particle traveled for 1 billion years to make that specific click?
So they're saying that's an assumption, an interpretation we built after the click.
That's the argument. A useful story, maybe, but built around the detection event, not the journey itself.
Okay. So if there aren't any photons zipping across space, what on earth is triggering our telescopes, according to this motion theory?
Right. So the theory suggests that when this rhythmic pattern, what we perceive as light, hits the sensor, it's not a particle impact. It's the moment that pattern becomes, let's say, stable or coherent enough at the detector to actually interact with its structure, reshape it momentarily.
Reshape the detector.
Influence its internal structure, yeah. And that resolution of motion, that stabilization, is what triggers the effects we measure.
Right.
Like electrons getting knocked loose, creating electron-hole pairs, shifts in voltage, charge building up, and all the things that make the sensor register a signal, a click, a spike, eventually part of an image.
So the effects are the same, but the cause is different. It's not the arrival of a particle, but the local resolution of this ongoing motion pattern.
Exactly. The click confirms the motion was resolved right there, right then. Not that a messenger arrived from far away.
Which means our telescopes, they aren't photon catchers. They're, what did you call them?
Structured motion resolvers.
Structured motion resolvers. That really is a completely different way of thinking about it.
It is. And it forces you to rethink other things, too, like what does photon counting even mean if there aren't particles to count?
Right, or brightness.
Well, the theory suggests this rhythmic motion comes in pulses or maybe like compression patterns within the flow. So a photon isn't a thing. It's more like a moment, a successful sync-up.
A moment of resolved motion.
Yeah. And brightness, then, isn't the number of particles hitting the detector per second. It's the rate at which the detector successfully resolves these incoming motion patterns. How frequently it achieves that sync.
Okay, the frequency of motion resolutions. Got it. So if we throw out the ancient traveling photons, what are Hubble and JWST actually seeing? What are those incredible deep field images made of?
According to this motion theory perspective, They're detecting variations within that fundamental motion field.
Variations like...
Different rhythms, different, I call them compression ratios, different structured patterns in space, gradients. But the key thing is, they're observing ongoing structure. Stuff that's being resolved right here, right now.
Not a picture of the past.
Not a relic from billions of years ago, no. It's observing the structure as it is currently resonating and being resolved by the telescope.
So those amazing Webb images, those distant galaxies, they're not snapshots from the early universe arriving late.
In this view, no. They're images of persistent motion structures. Structures that are still actively resonating, still shaping the motion field now in a way our telescope can lock onto.
Like tuning into a radio station that's still broadcasting.
Kind of, yeah. The underlying structure that causes the appearance of that galaxy is still active, still generating that pattern in the motion field that our telescope can resolve. That's why they look consistent over time when we observe them. The source pattern is stable.
Okay. That addresses why distant things don't just flicker out of existence. The underlying pattern is still there. So then what's the point of building bigger, better telescopes if it's not about catching fainter, older light particles?
Better instruments in this model give you finer resolution of the existing structure. They let you see more detail, more subtle variations, weaker patterns within that overall motion field. It's not about peering further back in time by catching older photons.
It's about seeing the present structure with more clarity, like upgrading from a fuzzy picture to HD.
Exactly. You're resolving the same fundamental ongoing reality, just with much greater detail and sensitivity, more nuance in the now.
So to sort of circle back this photon delusion idea, it basically argues that the photon concept, while handy, was always just an interpretation, right? Based on the end result, the click, not on actually seeing the particle fly.
That's the core argument, yes.
Yeah.
An assumption based on detection.
And the motion theory says, no, detection isn't an arrival, it's the finalization. The moment structured motion gets resolved right at the detector.
Precisely. It removes the need for these, well, almost magical messengers crossing cosmic voids for eons.
Yeah, no time-traveling particles needed.
Instead, you have this interconnected universe, this field of motion, and our telescopes are just sophisticated instruments that resonate with it. It's all about local interaction, local resolution.
Local resonance. And our tools are just getting good enough now to maybe perceive that underlying structure more directly without the old photon filter.
That seems to be the implication, that we're moving towards understanding a more fundamental layer of reality.
It really does feel like a potential paradigm shift, a different way of seeing everything.
It definitely raises some profound questions, doesn't it? If this view holds water, it changes how we think about space, about time, about connection, the very fabric of reality.
Absolutely. So maybe here's something for everyone listening to mull over. If the universe isn't just particles traveling through mostly empty space, if it's actually this continuous field of structured motion that our amazing telescopes are resolving effectively in real time, how does that fundamentally change our understanding of time itself, or distance, or even just the nature of reality that science is trying to describe? This idea of a motion renaissance, as the text puts it, well, certainly gives you a lot to think about.